Good evening, everybody. Welcome. Thank you all for making the efforts in the stormy weather, which has probably disrupted your travel. One of the reasons for starting on time is that just in case it's difficult for some of you to get back home as it was to get here, we're going to give you a little more time, so we're going to try to keep to time fairly tightly, and John, our speaker, is already aware of that. So thank you again, all of you who've made the effort to come this evening. I should explain who I am. I'm President-elect of the Institute of Physics. My name's Roy Sambles, and I happen to be Professor of Physics at Exeter University, and John and I have known each other for a very long time. Great privilege for me. I'm not too sure it was for John, but anyway, John, it goes back a few years. Can I remind you, please, to turn your mobile phones off? Could you do that now, please? Because we don't really want any disruptions. In about 1704, Isaac Newton published his book on optics. It's an amazing treatise. It's worth reading. If you can get hold of a copy, not of the original, but of the paperback version, it's well worth reading. And he, at that stage in his career, was 62. And it rather denies the suggestion that by the time you're 35, everything you've done is over and dusted. Well, John, likewise, who had already established himself as a key figure in theory of surfaces of semiconductors, actually probably has done his most formative work somewhat later in life. He had an amazing purple patch from about 1996 to 2006. And I'm not sure it's quite over yet. He's still very active in his research, which took him to the forefront of theoretical research in electromagnetism. Electromagnetism, of course, for those of you who aren't experts, is really how we function. We're electromagnetic objects, and it dictates much of our world around us. He did some key formative work in negative refraction, which is a strange concept, and he will explain it later on. Some really great ideas in transformation optics. Some really neat stuff in metamaterials. Metamaterials has burgeoned into a big area across the world. Plasmonics, and several other areas which he could mention. I don't know what you're talking about tonight, John. But he has galvanized the community across the world. If you look up the Web of Science, you'll find that his papers have been cited about 40,000 times, which is a staggering figure. And the papers you publish in your purple patch are all, near enough, not all of them, but many of them cited over 1,000 times, some as much as 4,000 or 5,000. The perfect lensing one, I noticed, is nearly 5,000 citations. So he has had an impact in science which is colossal. One of the giants of British science, to be honest with you. And it's absolutely fitting because of what he's done and its impact on electromagnetism, which optics was part of, and which Newton, in a sense, stimulated back in 1660-something and then published his book on in 1704. It's absolutely fitting that someone of John's stature, someone of repute across the world, has been awarded by the Institute of Physics the Newton Medal. And it's my pleasure, and it really is a pleasure, John, to ask you to deliver your Newton Medal lecture this evening. Thank you very much. Oh, and by the way, sorry, questions after the lecture, please, so that we can do the video. Thank you, John. Thank you, Roy. You may clap.
Well, thank you, Roy, for that. My ears are red already. It is a great honor to give the Newton lecture, named after our greatest, perhaps the world's greatest physicist. So it's a heavy burden indeed. I want to talk to you about some new ideas in electromagnetism. They have to do with new materials, metamaterials. They have to do with some new techniques which enable us to design these metamaterials. And along the way, there's some science which is very exciting and which has the great virtue that not all exciting science has, that it can actually be explained to school children. And one of the happy things I've been doing in recent years has been doing some outreach to school children who, of course, I'm only partly responsible for the fame of invisibility. J.K. Rowling has a lot to answer for, of course. So all these things I will mention. But let's start with way back. This isn't the beginning of optics by any means, but it's where I'm going to start today. So Snell and Descartes actually had the same idea about the same time. They told us how materials can be used to control light, and they formulated this law of how light is refracted at an interface. And we all know that lenses play a very important part in our lives, cameras and microscopes, telescopes, and so on. And Snell's law survives today because its great beauty is that you can think of light as just a stream of particles, and once you know what's going to happen at an interface, you can trace in your mind's eye how you might design some equipment before you even start putting the numbers in. You don't have to ask a computer for the answer until you want the details. Your imagination is free to roam, courtesy of Snell's law. But of course, Snell's law was formulated well before our current rather complete understanding of electromagnetism. Light consists, if you look on the microscopic scale, of electric and magnetic fields intertwined with one another, dancing from electrical form to magnetic form. And this dance was described by Maxwell in these very famous equations here. Although Snell's law is very intuitive and works at the everyday level, once you get down to a length scale that is comparable with the wavelength of light, then you really do have to switch to the ingredients of Maxwell's equations, which are the electric and magnetic fields whose behavior he describes. And to describe this, we introduced, our aim was, of course, Maxwell's equations do describe the behavior of light very accurately, but I challenge you to stare at these equations and then ask how light would refract at an interface. It's not obvious, yes, and it is true that you can give these equations to a computer and some boundary conditions, and it will tell you the answer. But what they do not give immediately is an understanding of why that is so. And so we wanted to formulate a way of looking at Maxwell's equations that was as intuitive as Snell's law. And so we picked on the ingredients of Maxwell's equations, which are electric and magnetic fields. And Faraday represented these by lines of force. And so each field can be represented by a line, which indicates the direction of the field, and the density of lines, which is not shown here, but if you have many lines close together, that means an intense field. And that's a bit like rays, except that you're now describing the accurate ingredients of Maxwell's equations, the fields, the electric and magnetic fields. And what we realized was that if you imagine that these field lines are embedded in some sort of space, and then you distort that space, and think of that as a coordinate transformation, then the field lines you imagine are moved with this rubber sheet, which you're thinking of space as being like, and so you can distort the passage of the line by distorting space. And actually that's a way that Einstein thought of these things. And from this distortion of space, you can derive a formula for what the refractive index, or if you would like to be precise, epsilon mu, should be to make these field lines go in this direction here. And so that's the basis of transformation optics, which is the design theory behind the concept of metamaterials. So this is the old Descartes-Snell law. This must be a talk I gave in France because I call it the Descartes law. And here's the new law, which applies not just to rays of light, but applies to electric and magnetic fields. And if this matrix lambda is a matrix of the first derivative of that coordinate transformation, this tells you how epsilon and mu change. I don't have time to describe it here, but there is an intuitive way that you can actually crawl over this mesh and discover at each point how epsilon and mu change, just without doing any differentiation with a ruler. So that's the design technology, and the things we're designing are these things called metamaterials. Now, it turns out that in electromagnetism generally, and in optics in particular, there are many material properties which you think might be allowed in terms of the laws of physics, but you just can't find those properties in nature. And if you want to build some equipment or do something in optics, you have to build it out of a material, and if the material isn't there, you can't do it. And so we introduced this concept of a metamaterial. Now, an ordinary material, it responds to an electric field, say, according to how the atoms and molecules polarize, and its average response over many millions of molecules gives the electrical response of glass or water or whatever common material you're thinking of. But in a metamaterial, the atoms and molecules are replaced by slightly larger elements which have a physical structure. They might be tiny metallic rings, for example, or holes in the structure, the very, very simplest form. And in these metamaterials, these little units, which are bigger than atoms and molecules, but nevertheless smaller than the wavelength, they act like rather big atoms and molecules. And you, by designing their structure, you can design the properties of these metamaterials. And because you're not limited by the periodic table, by the chemistry, you can add to the chemistry the flexibility of structure. And in this way, you can design into these materials properties which have never been seen before. in natural materials. And I'm going to give you one or two examples of these materials. The first ones were made to work at radar frequencies by Mike Wiltshire, who was working at the Marconi Company then. This all originated from a consultancy I had with the Marconi Company. And here he's making a material to respond to 10 centimeter radar waves. And these structures are about 5 millimeters across, much less than the wavelength of radar waves, but still large enough that you can engineer them quite simply. And you can see that they're in the form of a ring. And so if you put a magnetic field normal to that ring, it induces a current in the ring. And that in turn produces a magnetic field in response. So this is magnetism without magnets. And if you start to do something slightly fancy, like snip the rings off here, so the ring isn't complete, that makes a little resonant circuit. And as you tune through the resonant frequency, you get a whole spectrum of very different properties from this material. The most striking of which is that at some frequencies, the magnetic response comes in the opposite direction from the applied magnetic field. And that was one of the early fascinations of these structures, negative magnetism. And here's an exploitation of that made by David Smith, who has been my very long-term collaborator and friend in all this. David's both an experimentalist and a theorist. I'm just the theorist. And he took this concept of metamaterials and he made these split ring structures, which have been designed for the Marconi Company, and made them into this two-dimensional structure here. And this wire is on the other side of the circuit. So these rings give you negative magnetism, and these wires give you negative electrical response. Now, it turned out that that was the prescription given many years ago by a Russian scientist called Veselago. And he said that if you could have negative electrical and magnetic response, then something remarkable would happen. That this material will become transparent to electromagnetic waves, and the refractive index would be negative, the third negative. And he had already explored theoretically what fascinating things you could do if you had a negative refractive index. And this was the first structure ever that had a negative refractive index. Well, it turned out the funding ran out for radar waves, but there were some friendly MRI scientists willing to give us money at Marconi. And this was a Swiss roll structure, which is a coil of insulated copper sheets wound round into a resonance structure. And these were designed to have a resonance at 21 megahertz, which is one of the frequencies used in MRI equipment. And the idea of this was to guide magnetic fields down the center of this rod. And I might come to that later in my lecture in terms of applications, because there have been some applications of ideas related to that. Yes, so just very briefly explaining what negative refractive index is, Victor Veselago's idea. So this is what glass and water do, and when light goes into glass or water, it comes out this side of the normal. But if it goes into a negative refractive medium, it comes out the opposite side of the normal. And so by this definition, this angle is negative, put it in here, and you get a negative refractive index. Now, stated so simply, that seems merely like a mathematical anomaly, nothing very special. We know about negative numbers, but if my lecture runs to time, I will tell you about some of the really remarkable consequences which follow from negative refraction. And here are some of the structures which people are making to show negative refraction. Here's a metamaterial on a much finer scale here. This is a layered structure called the fishnet structure, and the layers have a thickness here 30 nanometers, much smaller structure. This is designed to work at optical frequencies, much shorter wavelength, therefore the structures have to obey this law of being smaller than the wavelength, so they're very small. Here's a micron. And by layering silver and an insulator, magnesium fluoride, you can make this structure with a negative refractive index. This work was done by Chang Zhang's group at Berkeley, California. So that's a negative metamaterial working at optical frequencies. So when we assembled these tools, and we're very excited about them, we asked ourselves, how do we explain these to a wide audience and show that audience that what we have is profound and exciting, as we believed it to be. Now, I think you might not get terribly excited by that slide. And in particular, you might not have got very excited about these equations here. But what we decided was to find something which you could do with these materials and with these equations which hadn't been done before, and which would surprise people, make them wake up, and perhaps pay attention to the less sensational things. And the target we chose was invisibility. Now, this is Peter Pan, his statue in Kensington Gardens, just north of my college. And what this slide is to show you is that if you want to make something invisible, it's not enough to make it black. If you make it black and it's in a bright environment, such as a squash court and a black squash ball, you will be very much aware of it, because what you'll be aware of is the shadow of that object. And it's Peter Pan because he's a little boy who lost his shadow. And when an object has lost its shadow, it is truly invisible. So how do you do that? Well, the idea is quite simple to be stated. So you want to take a region which you're going to hide, so you can do anything in there that you like and you will not be seen, and the observer will not be aware that he's not seeing you. And you're going to hide that region by means of a cloak, which is going to be of finite extent and wrapped around this hidden object. And the function of the cloak is to grab the rays of light and steer them away from the hidden object, so you never see it, but also return them to the path which they had before their path was disturbed. So the observer standing here sees what's behind the object and is unaware of this deviation which has been made. Now, I think you can see that this technique of transformation optics, which I outlined to you, is ideally suited for this, because here's a coordinate system, and inside this cloak here, I'm going to distort the coordinate system, tear a hole in it, and push the coordinate system out, and taking with it the rays. So the rays follow the distortion of the coordinate system and avoid the hidden space. If you don't distort the coordinate system, the rays don't move, and you do not, therefore, change epsilon or mu, the refractive index. And so this technique is ideally suited to designing a cloak, because if you don't mess with the coordinate system, then you don't disturb the ray. So this ray stays where it was, and this ray comes in as it did before. And it's only in this region that you need tune the parameters. And you go to the equations, which are straight from Einstein, and there you have your cloak. So here's the simplest possible cloak. You tear a hole in the space and you squash all of this material inside this sphere or cylinder, whatever your choice of cloak, so that you now have created a hole and compressed space and all the rays with it into this region here. This simple algebraic formula tells you how you might do that. There are many different ways you can compress space, of course. And when you've done that, the rays will look like this. And actually, that idea, once you have this notion of transformation optics, that idea is so simple and easy that I thought of it as a joke. And I was invited to a DARPA meeting in San Antonio some years ago, and they said, your job is to ginger up the meeting. So I, blah, 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 metamaterials, and I thought, I'll finish with a joke. I'll tell them how to design a cloak of invisibility, and expecting a laugh and sit down. And the joke fell rather flat. Everybody looked deadly serious, and then they started muttering to one another. I thought, I've trodden on some bad ground here, but not so. It turned out that they were very excited, and certainly they offered me a lot of money after the meeting to do some research. And if you think about it, I mean, this idea is really, really simple. Like, you want to do this, but the idea of invisibility is something which we find magical. Children find it magical, and that's because the notion of light traveling in a straight line is embedded in your brain. And so when that notion is disrupted, however simply, we're surprised. Actually, light doesn't always travel in a straight line. This is a mirage in the desert, and it comes about because of hot air on the desert surface, which is less refracting, less dense, and therefore less refracting than the cool air above it. And the gradient in refractive index means that the light travels in not a straight line, but a curved trajectory. So it may reflect the light so that you appear to see the sky reflected in the desert. Here in the UK, we're more familiar with these road mirages, where hot asphalt seen in the distance appears, even on a hot day, to make the road seem wet. So light is known to travel in a curved line. And here's the first shot at making a cloak done in David Smith's laboratory in 2006. And it's an old slide, it's not got the date on it. And what he's done here is to use metamaterials to deflect radar waves, the cloak radar waves. My pointer isn't so good. And this is the gradient in the refractive index of the cloak as you go from the outer to the inner region. And that's achieved by altering the physical structure of these little metamaterial elements here. That's very easy to do. And you don't even have to make these in your own laboratory because they're elements of a printed circuit board. So you design them on your computer, you write off to a printed circuit company, and back comes your metamaterial in the post. And that gave the subject a flying start. Well, that was the first cloak for radar waves. I don't have time to show you the results. They're rather old hat now anyway. But then we had the thought that what people really want is a cloak for visible light, and that's much harder because even with metamaterials, to get the flexibility and the properties that you need to design a cloak is very difficult. So we thought, well, how can we make the cloak easier to build? And Jensen Lee, my postdoc at the time, from Hong Kong, worked with me on some new ideas there. And it's a matter of geometry. So there are actually three ways you can imagine making a cloak. So you can think of a cloak as a sort of lens. Now normally lenses have the task of making something appear bigger, but you can also make lenses that make something smaller. And if you made a lens that made something very, very small, that thing will be invisible. So a cloak can be thought of as a lens which makes things inside it look infinitely small. Now, there are three ways that you can do that. You could have a vaguely spherical cloak, and it can crush the contents of the cloak to a point. Or you could have a cylindrical structure, and objects viewed through at the center of that cylindrical structure will be squeezed into a very, very thin wire. A point's invisible, a very, very thin wire is also invisible. I think you catch my drift. A third way is to squash something really, really flat. Now when you do that, it becomes very, very highly reflecting, actually. So what you have is a very, very thin sheet, and that isn't invisible. Only if you look at it edgeways on. That's the only way it's invisible. It's all two-dimensional. But there is a way you can make it invisible. I've asked this question so many times in lecture, I never get an answer. Where would you make a mirror invisible? Where would you put it to make it invisible? Obviously nobody's been to this lecture before. So the way you make it invisible is to put a mirror on another mirror. Okay? So mirror plus mirror, still a mirror. And there are many situations, particularly in radar, where the ground is a good conductor and a good reflector, where you're working in an environment where you have another mirror on which you could hide something which was a flat mirror. And so this was what we call the carpet cloak, hiding under the carpet. So what Jensen has done here is to take something which was flat, and he's compressed space here. And the various ways you can do this is a quasi-conformal way in which the little cells retain their shape. And this region becomes more refracting as you compress it. And you can use the usual formula to tell what is the refractive index of that material there to make a cloak. And this cloak was taken up by the Berkeley group. Here are some simulations of the cloak. If you have a reflecting surface and then you just make a bump in that surface without cloaking it, then that bump becomes very visible to a ray of light coming in because the facets on the cloak produce two reflections instead of a single reflection, as would be the case for a flat mirror. And here you put a cloak in place and you've still got this little bump down here, but cloaked, and you get a single reflection. So the cloak has in fact made that bump appear as though it's a perfectly flat and thin mirror. Now this cloak was built at the University of California, Berkeley laboratories, and what they did was this is a two-dimensional cloak again, and here is a silicon slab acting as a waveguide, and here's a piece of metamaterial where the refractive index is constant, less than the surrounding, and they've achieved that in a very, very simple mechanism. They just drilled holes in it to make it less refracting. And then when you come to this region here, which is the cloak,
the density of the holes becomes less. So this region here is more refracting than this region out here, and in just such a way as to reproduce the parameters of the cloak. And so this mirror bump in the mirror here is hidden from view by this surrounding cloak. Here's an electron micrograph of the cloak. The dimensions are 1 micron, so it ain't a very big cloak, but and the bump is about a micron across. Here are the parameters of the cloak. And the data, now I forget which is the theory and which is the experiment here. It doesn't matter, of course, they agree with one another. I think this is the experiment. So you have a flat mirror, and of course it reflects a single beam. So when you measure it, you just see one Gaussian beam of light. But if you put a bump on that surface with reflecting facets, you get several reflections from the bump, and that's indeed what you see. But finally, if you make a cloak in that silicon mirror and send the light in, then you're back to what appears to be a flat surface, but it isn't. It's a bump with a cloak over it. So that proves the concept of optical frequencies. But one of the things we're proud of with this design technique of transformation optics is that it's accurate not just at the level of the rays. This cloak is big enough that you could have designed it with ray optics. The transformation optics techniques also is accurate at the level of field. So you should be able to design a cloak where these lines represent not rays of light, but the field lines of a magnet. So here's the north pole of a magnet, and here are the field lines coming out, and you should be able to design a cloak which steers the field lines around so that the outside field is undisturbed, and the bit in the middle is cloaked so the fields never reach it. Now this is quite different from a shield. Those of you who do experiments with magnetism know that there are things, the materials called mu metals, which can wrap around an object, and they will grab the field lines and steer them away so that there's no magnetic field inside that shield. But the price you pay with these materials is that they also create outside the shield a very large dipole field, and there's an enormous force in a strong magnetic field on the shield, and at the same time there's huge disruption of the field itself outside. But a cloak is quite different, because a cloak does the shielding job, but at the same time it leaves the field outside undisturbed, so you cannot tell the cloaking's place, and therefore there is no mechanical force on this cloak, and because there's no disturbance of this field, any experiments like an MRI experiment which rely on a uniform field is not disrupted. And Ben Wood and I worked on the concept of this cloak in 2007. And the challenge was that the parameters of the cloak demand a material which is anisotropic. And it demanded that if you put a field on in one direction, you had a permeability greater than 1, a ferromagnetic material. And if you put a magnetic field on in the other direction, you wanted a permeability which was less than 1. Now, ferromagnetics are well known, so that side of the problem is well addressed. But although magnetism where mu is less than 1 is known, that effect is very, very weak in all materials. So if you had a material which was diamagnetic and its mu was 0.95, that would be a really strong diamagnetic material. But we're demanding diamagnets with mu of 0.5 and less, unheard of, until metamaterials come along. And this is the way you design that material. So these are superconducting plates, and superconductors expel magnetic fields. Magnetic fields penetrate only a very small distance into a superconductor. So if you want to send a field in this direction, it's got to squeeze its way through these very narrow gaps, and that costs energy, and that means that this material in this direction is acting like a diamagnet. This squeezing of the field lines creates a strong diamagnetic effect. And so here's, in some units, the side of the plates and the number of layers of plates. And the key thing is the spacing between the plates, because that determines how much the fields are pinched. And as the spacing goes down, the permeability decreases from 0.64, 0.23, and then eventually down to almost 0 as the plates are pinched together. These are numbers which you can never find in nature. And our experimental group made this system. They deposited lead on a microscope slide, and then they scribed the lead so that it was in little squares. Lead is a superconductor if you cool it below helium temperatures, and these are their measured permeabilities normal to the sheets. And you see there's very good agreement, so this metamaterial really does its stuff. And without it, you couldn't design this cloak. So here's Ben's design for the cloak. The ferromagnetic stuff gives you a large permeability in this direction. The sheets are thin, so the field lines are unimpeded by the sheets traveling in this direction. But if you take a field going in the radial direction, they have to squeeze through these little gaps, and the mu in that direction is reduced. Now there the matter rested until a year or two ago, and some guys in Harvard took this up, these people here, and they actually built this cloak. So here are the scribed sheets with the gaps between the superconducting plates, and they didn't actually use a ferrite, they used chromium to give you the mu greater than 1, and in this way they were able to build a cloak. And they tested the cloak by putting it in a magnetic field created by 2 coils. Okay, so a magnetic field is traversing the cloak. And then they sensed the magnetic field. They have many, many sensors, but I'm just going to show the data from 2 of their sensors. This is a sensor inside the cloak, which tells you whether or not the field has been removed there. And this is a sensor outside the cloak, which tests whether the field remains constant there. And here are their data. So this is what you want to happen. The cloak should grab the fields and just as the original cloak did with rays of light, transmit the fields to the other side without any disturbance external to the cloak. And here are their data with no cloak. So if you put no cloak there, then the field ramps up uniformly with a current through the electromagnet, obviously. But if you put a cloak in place, the field inside the cloak remains 0, whatever the current. So it's doing the job of screening that internal region there. Now if you look at sensor 2, what you see is that for all the currents measured, the magnetic field outside the cloak is exactly the same as it is inside. And therefore the cloak is doing its job. It's screening the interior, but outside you don't know that that's happening. You just see a constant field of whatever's happening. So that, I think, was a very nice confirmation for us that the new technology which replaces Snell's law, which only works for rays of light, is much more general and operates at the level of the field lines. In particular, it can design a cloak for magnetic fields, and it can do much more than that. That's just a demonstrator of what it can do. So in the last few minutes of my lecture, last 20 minutes, I want to return to this subject of negative refraction. Because although it's not on the face of it as immediately sensational as a cloak, J.K. Rowling hasn't written any novels about negative refraction, so we're at something of a disadvantage there. But to my mind, it's the more remarkable effect of the two. So why is it remarkable? Here is what Beslago predicted for negative refraction, and why should it matter that the light goes this way rather than that way? Why is that so surprising? Well, let me suggest to you that you can actually use this effect to focus light. So if I got a point of light here radiating rays, and they bent back towards the axis of the lens, then you can imagine they form an image here. But they do it in a very curious way. So if I have a source of light inside the material, then this negative refraction will produce an image outside the material there. So if I had a swimming pool full of negatively reflecting material, then the contents of the pool would appear to be floating above the surface of the pool. Very strange. Health and safety mechanism. If your kids were in the pool, you could actually see what they're up to floating above the surface of the pool. So that's one thing. Now, I want to combine this idea of negative refraction with transformation optics. So you might think, well, that's really quite interesting, but what else can we do here? I mean, that's a flat lens, an object which is the same size as the image. You might want a lens which makes something bigger. And transformation optics takes space, transforms it, bends it, squeezes it. So I could take that space and I could transform it so that this flat slab of material became a cylinder or a shell of material. And at the same time, that would make the image larger relative to the object, because I'd be squeezing the lines in order to turn this into a shell or a cylinder. And then you get a lens like this. Now, I should explain that there's something else rather curious about this lens. And it's the following, that if you, actually I can best do that by snitching some slides from later on. Okay. So here's a slab of negative refracting stuff acting as a lens, and Veselago taught us that this could happen, that it does act like a lens. But in the year 2000, I realized that this lens was rather special. Most lenses, or all lenses that we've known to that point, were limited in the resolution by the wavelength of light that you use to use them. And that is about a micron. And many things that you really, really like to see in biology are below the micron length limit in size. But it turns out, when I looked at the properties of this lens, that it isn't limited by that law. If you do the mathematics according to Maxwell's equations, then it turns out that this focus, providing you build the lens perfectly, the focus is perfect. That caused a lot of fuss at the time. Now, one way of understanding that is to go back to a statement I made at the beginning of the lecture, and that is that Einstein said that when the coordinate system is distorted by a gravitational field, for example, then the metric changes. So if you compress space, the metric gets larger. And that's just the measure, is the metric, of how much you've squashed space. And what's more, I said that when you write Maxwell's equations in the notation that Einstein uses for general relativity, you find that his metric comes in the same place as does the refractive index. So you don't have to find a neutron star. You just have to find the right refractive index to change the metric as far as light's concerned. But here's a paradox, because what if you make something with a negative metric? And pardon me whilst I do my origami here. So many of you will have seen me do this before. So I'm going to make the simplest compression of space possible. I'm going to take a little region of space like that, and I'm going to squash it. And as I squash it, the refractive index goes up. Of course, the metric increases. And I can squash it till, the refractive index is infinitely positive. And then if I'm a mathematician, I can squash it a bit more. Like that. Now that's a really weird space. This space you can understand, yes, but this is really weird, okay? Because if you've got something which is sitting here, the light sees it once, twice, and three times. So when you squash space like that, you've actually created, inserted into space three manifolds, if you like. The space is convoluted, and it has these three values here. And you do that by creating this region here where you compress space up to infinity and then down to minus infinity. This is negative space, optical antimatter. It annihilates space which is next to it. And so what you think the light is doing is going along here. What the light thinks it's doing is going along this trajectory here. And therefore, this object is seen 3 times by the light. Now that description is accurate at the level of Maxwell's equations. And so the seeing of this object is not an approximation in the ray approximation. It's exact at the level of Maxwell's equations, which knows nothing about the limitations of the focusing of light by the wavelength. And therefore, this object, this image, is the object and is therefore perfect. So this lens is a perfect lens. And that, incidentally, is why a negative refractive index is such a strange and mysterious thing. On the face of it, this way, that way, what does it matter? But when you begin to look into the consequences of that are quite profound. So here we have the lens made into a magnifying glass. It's a perfect magnifying glass. And what it does, it takes the contents of this inner region here, and when you view them from outside through this now circular or spherical lens, the contents appear to be contained within this larger sphere here. And here's a bit of maths to go with it if you're interested. So you can make a small object appear bigger than the lens itself, magnify it so it's bigger than the lens itself. And why is that strange? Well, I normally have a glass of water. Glass of water, I guess. Right. Have you ever noticed this? You look at a bottle of water, the water appears to go right to the edge. You can't see the glass. And the reason for that is very simple, that any ray of light which strikes this bottle must go through the water. So if it were filled with milk, it would be even more surprising. The white of the milk would go right to the edge of the glass. And that's just a simple exercise in refraction, very easily understood. You do ray tracing, every ray passes through the water or the milk, and therefore goes to the edge of the bottle. But now, what if this bottle was made not of glass, but of this negative refracting stuff that I have here? Then the milk or the water would go not to the edge of the bottle, but here. It would appear as though the milk was in a very, very large bottle like that, which is very strange. Let me show you just how strange that is. Here I'm doing a ray tracing. Remember, the ray approximation is an approximation. Okay, so here I've got a negative refracting lens. The light goes through. Every ray of light which strikes this big circle, according to Maxwell, should be compressed into this inner circle here. It's looking good. They're all going in. Oops, problem. This ray of light doesn't hit the lens. They're according to the laws of Snell's law, ray approximation. How on earth can you capture this remote ray of light? But here's a solution of Maxwell's equations. And here the incident ray is expressed as a series of wave fronts, and you can see that these wave fronts are grabbed and forced into the central region, just as Maxwell, as the theory says it should. This is a solver, computer solver for Maxwell's equations. And so this is a very strong statement of how transformation optics predicts things which are just not in the book of the ray approximation, and demonstrates how very strange and remarkable the phenomenon of negative refraction is. So what can you do with this? Well, there are devices in optics that only work if they're really big. And one of them is a parasol. A parasol creates a shadow to shade you from the sun. And that works because the parasol, creating the shadow, is much bigger than the wavelength of the light. If you tried to make a really tiny parasol, which was a micron across, comparable with the wavelength of light, it wouldn't create a shadow. The waves would diffract around that object and rapidly fill in the electromagnetic field on the far side of the object. You cannot create very, very small shadows. Or you cannot create shadows of very small objects. However, using this lens, what you can do is to put a very, very small parasol in here and make it appear like a really, really big parasol, much bigger than the original parasol, much bigger than the lens itself, and this big, okay? So you could make a parasol which appeared to be bigger than the wavelength, even though it wasn't. And this is a computer simulation which shows a black object inside a negative refracting magnifying lens. And so outside the blue stuff, there's nothing. And here you see a ray of light or hitting the object, and it's actually creating a shadow which is much bigger than the original object, than the cloak, and as big as it's predicted to be by this guy in here. So metamaterials, transformation optics, negative refraction, some very surprising things, some results which took me a long time to understand, and which some people in the community have never accepted. People still write papers saying negative refraction is rubbish, perfect lenses don't exist, and so on. I got to the stage where I take it all on the chin, but it was really rather hurtful when you wondered whether you were right or not in the beginning. But at the end of the day, you can have as much fun as you like with amusing mathematical theories, but at the end of the day, what matters in physics is if you, first of all, if your theories can be realized in experiment, and then after that, if the experiment can go to produce something which is useful for society. And that takes a long time, and the more profound the idea, the longer it takes. You only have to think of the laser, what a profound idea that was, and how long it took us to get to the state where we are today, where the applications of lasers are so diverse and so very, very imaginative. Academically, there's no doubt the metamaterials have taken off. Here's the somewhat rapid rise of metamaterials. This is the items published in each year and the number of citations in each year. 2013 obviously isn't completed yet, so we don't have the citation data in full for that. So there really are a lot of people working in this area, and they're working on it because it's so exciting, but also because it's now being seen to be very useful. So I'll give you some instances now in my last couple of minutes of the applications. So here is an outfit which gathers patents. Intellectual Ventures is based in Seattle. It's owned by Nathan Myhrvold, ex-scientific director of Microsoft, and they hold most of the patents on metamaterials. And they are producing a company called Chi-Meta, which they've just spun out with, it's now capitalized to $50 million, I think. And what they're doing is using metamaterials to create a phased array, which is used to communicate with satellites for a SATCOM's phone. Now, people do that already, but the kit they use is a dish which is about 30 centimeters in diameter. In order to focus the beam on the satellite, it has to be that big, and it's mechanically steered to track the satellite. It's expensive, it's heavy, it consumes quite a bit of power. The metamaterials concept has no moving parts, and it steers where the receiver points to electronically, because the metamaterial can be tuned in a very cheap and simple way using a DC current. And here's the prototype hotspot which they're creating, which will look something like this, 30 centimeters on its side. Their target price is under $1,000. It's very light. It will plug into the USB port of your laptop, and that you should be seeing those coming on the market quite soon. This is again something which is very simple. This is a lens for focusing radar waves, and instead of a big chunk of polythene which we'd normally use to focus radar waves, 30 centimeters in diameter, very heavy, several kilograms, you can do the same thing with a very thin sheet of metamaterials, a graded index lens, and that will do the same job. In fact, it gives a better focal spot than the polymer lens. And this is used in radar, can be used in radar, and Toyota are thinking about putting it in the collision avoidance radar to focus terahertz radiation. MRI. My colleague Richard Sims is working on a problem in MRI. If you want a very accurate MRI scan of your heart or your liver, what you do is to put the pickup coil, which senses the very tiny magnetic signals from the nuclei, which tell you what's going on there. You want to put that coil very close to the heart or the liver. And the way that's done is to make an incision in your vein, down near your legs, push that coil up the vein with wires trailing behind, and then it gets near to the heart and you can do a very precise MRI scan. The problem with that is that you're turning the magnetic signal into an electrical signal, which then travels down a metal wire, which is about 1 meter long, from here to here. That's about the resonant length at the frequency that MRI scans are done inside the body. And it can get hot. If it gets too hot, it sticks to the side of the vein, and that's not nice, as you may imagine. So a more safe version would be to, if you could, define design a wire which instead of turning this magnetic signal into an electrical signal, kept the magnetic signal and transfer the magnetism along the magnetic wire. Now this is exactly what Richard has done. Again, it's not as impressive as invisibility, but this magnetic wire here, which consists of little metamaterial elements which allow the magnetic field to hop along its length, this is totally safe because it is not an electrical conductor and it does not get hot when you put it in the RF field. So that's another application. Richard is trying to found a company to patent and sell that kit. So I hope on this journey through metamaterials, invisibility, and transformation optics, what I've shown you is that this ancient subject of optics is full of life and surprises, even at this several thousand-year-old stage of its life. And that as well as the things which astonish scientists, there are things which can astonish the general public, even school children, and at the same time, these astonishing things are being turned into products which will help us in our everyday lives. Thank you very much for your attention.